Welcome back to another explainer. Today, we're taking a look at a really fascinating paper titled Acceleration of Deep Neural Network Training Using Field Programmable Gate Arrays. We're diving right into how researchers are finding ways to accelerate AI training while drastically cutting down on power consumption. Before we even look at the roadmap, let's stop and ask ourselves a really fundamental question. Why is training these massive neural networks pushing our traditional computer hardware to its absolute limits? I mean, we all know AI is doing mind-blowing things, but what is actually causing that massive bottleneck behind the scenes? All right, here's our roadmap for today. We'll hit the AI energy problem, look at what an FPGA actually is, peek inside a CNN, shrink some math with quantization, streamline the architecture, and finally look at faster speeds with lower power.
Okay, section 1, the AI energy problem.
So the real bottleneck here? Deep networks, especially those massive convolutional neural networks, have literally millions of parameters. And you know what that means? They need a ton of memory. This creates a huge memory bandwidth limit that completely throttles computational speed. The research points out that just shuffling this massive volume of data back and forth to external memory is a huge energy drain. Actually, just accessing the RAM costs way more latency and energy than doing the math itself. And yeah, traditional GPUs are great at maximizing throughput to handle all that math, but they're total power hogs trying to muscle through those memory bottlenecks. Moving on to section 2. What exactly is an FPGA? Let's define it. An FPGA, or Field Programmable Gate Array, is basically a semiconductor built around a grid of configurable logic blocks. And the absolute magic here is that they can be physically rewired and programmed after they're manufactured. Think of it less like a rigid, locked-in microchip and way more like a custom factory. You can literally rewire the assembly line to perfectly match whatever mathematical task you throw at it. This really gives you a great look inside that factory. You've got these configurable logic blocks, or CLBs, acting as your reprogrammable workstations. They've got smaller components inside, like lookup tables and flip-flops, and they're all hooked up via a super flexible grid. And since you can program it with everyday high-level languages like C or C++, you can customize the hardware directly to the specific neural network algorithm you're running. It's brilliant. Section 3. Inside the CNN. Let's break down how this actually builds up. First, data flows right into the convolutional layer, which extracts features from an image using some incredibly intense 3D multiply accumulate operations. Next, we hit the ReLU layer. That's an activation function that just snaps any negative values right to 0, which helps it converge a lot faster. After that, the data gets shrunk down by the pooling layer. It downsamples the info to cut down on dimensions and save compute cost. And finally, the fully connected layer swoops in to combine all those extracted features and categorize the final output. To give you a clearer picture, think about how the pooling layer downsamples an image. It basically just grabs the most prominent feature from each regional section of the grid. It's a really simple trick, but it drastically reduces the amount of data and therefore all the redundancy that the hardware has to deal with in the next layer. It stops overfitting and saves a ton of compute time. All right, section 4, shrinking math with quantization. When we compare these two mathematical approaches, there is just a massive opportunity here. The gold standard in deep learning is usually 32-bit floating point math. It gives you incredible precision, sure, but it demands huge memory bandwidth and guzzles power. On the flip side, we have 8-bit fixed point. The researchers discovered that stepping down from 32-bit to 8-bit math creates massive energy savings and memory reduction. And get this, there's only a tiny, basically negligible 0.77% drop in accuracy for a really complex model like AlexNet. No way, right? So the big takeaway here is that quantization is essentially like packing lighter for a trip. You might leave behind a tiny, almost unnoticeable fraction of detail by rounding those numbers down to 8-bit. But man, does it pay off? Your data just flies through the hardware's memory much faster, it enables high memory cache usage, and you use a fraction of the power along the way. Section 5. Streamlining the architecture. So first, the researchers actually tackled the assembly line itself with a single kernel design. Older hardware accelerators would use completely different kernels for the convolutional and fully connected layers, which just chewed up FPGA resources. But here, they totally repurposed the assembly line using one unified kernel for both. Since fully connected layers are essentially just multiplying and adding anyway, they just treat them like convolutions with a flattened input. This means the FPGA doesn't have to waste precious time or memory constantly reconfiguring itself. They also brought in SIMD, that's single instruction multiple data. Instead of painstakingly handling data one single piece at a time,
Simd lets the system fire off one instruction that triggers multiple parallel actions all at once across the data flow. It's a real game changer because it massively boosts processing speed, and the developers don't even have to manually rewrite the kernel code for every single operation.
Looking at the whole package of optimizations, we've got the reused kernel for both layer types, we've got loop unrolling, which maximizes those parallel computing units and completely gets rid of queues. We're caching global data locally to avoid those super slow, expensive trips to external RAM, and we're vectorizing output features along the end dimension to squeeze out maximum data parallelism. It's exactly this specific combo of software tricks that finally lets the FPGA smash through those classic memory bottlenecks. Finally, Section 6. Faster speed, lower power. Looking straight at the numbers from the research, the trade-offs are super clear. The AMD GPU wins on pure raw speed, pushing over 280 giga operations per second, or GOPS. But, and it's a big but, it's chewing through 94.5 watts of power to do it. Now, look at the DE1_SoC FPGA. The difference is absolutely wild. It only needs 18.5 watts. That gives it a massive energy efficiency score of over 11 GOPS per watt. And that brings us to a really important number, 203.75. Because of all those brilliant hardware and software tweaks we just talked about, this FPGA hit an impressive 203.75 GOPS while running the AlexNet model. So it's still highly competitive with the GPU on speed, but it's playing a completely different game when it comes to power consumption. But if you take away one number today, make it this one, 22.6x. When you actually crunch the numbers on that energy efficiency, this optimized FPGA is a staggering 22.6 times more efficient than the traditional CPU they tested against. And it's nearly 4 times more efficient than the GPU. As the researchers put it themselves, FPGAs could obtain greater power or energy efficiency than GPUs. Compared to the CPU and GPU, our design is 22.613x and 3.709x more energy efficient, respectively. The main takeaway here is that by combining that custom factory, reprogrammable nature of the FPGA with incredibly clever software tricks like 8-bit quantization and a single kernel architecture, we can actually pull off these massive efficiency leaps. And we do it without sacrificing the heavy-hitting performance we need to train deep neural networks. So this explainer really leaves us with a massive question for the future of the industry. As AI models just keep exploding in size and complexity, is the future of hardware really about endlessly chasing raw, brute force power? Or is it about mastering brilliant efficiency? Are we just going to keep building bigger, power-hungry data centers? Or are we going to start packing lighter and building smarter, reprogrammable factories? It's definitely something to chew on. Thanks so much for joining me on this explainer. I hope you found it as absolutely fascinating as I did.